Welcome to module number 3 of this course on RF and microwave, brought to you by the Comtech Academy. We will be focusing on two-tone driving and intermodulation in this video. Two-tone driving applies an input signal, Vint, to a two-port. This signal consists of two sinusoidal signals of the same amplitude. The formula shown is valid for the input signal. Inserting the two-tone driving signal into the nonlinear transfer function, represented by the Taylor series equation, results in intermodulation products at the output. The angular frequencies ω1 and ω2 are specified in terms of Fin1 and Fin2, respectively. New frequencies are generated due to trigonometric conversions. These conversions are responsible for the second and third harmonics shown in the formulas. These other trigonometric conversions yield the second and third order intermodulation products. Refer to the formulas for more details. This table summarizes the intermodulation products up to the third order that result from two-tone driving. The DC component of the intermodulation products is given by the formula shown here. These are the formulas for the fundamentals in the output spectrum. The second-order harmonics are calculated using the formulas presented here. The second-order intermodulation products are given by these formulas. Here are the formulas for the third-order harmonics. Finally, the third-order intermodulation products are calculated using these four formulas. This illustrates a two-port system, which is a nonlinear amplifier, being driven by a two-tone signal in the frequency domain. This chart represents the output spectrum of the nonlinear two-port with two-tone driving, showing intermodulation products up to the third order. This is a spectrum analyzer display of the intermodulation products up to the third order from a nonlinear two-port with two-tone driving. Besides generating harmonics, two-tone driving also produces intermodulation products, sometimes called difference frequencies. The order of these products is the sum of the order numbers of the components involved. For example, 2 + 1 = 3. The frequencies of even-numbered intermodulation products, such as the second order, are far from the two input signals, located at the sum and difference frequencies. They are generally easy to suppress by filtering. This image illustrates the third-order harmonic band. Even-numbered intermodulation products are usually easy to suppress by filtering. Some odd-numbered intermodulation products, known as difference products, always occur close to the input signals. This makes them difficult to suppress through filtering. This spectrum analyzer display shows odd-numbered intermodulation products that are difficult to suppress by filtering because they fall in the in-band region. Depending on the application, both even and odd-numbered order products can cause interference. In cable TV amplifier measurements, where the frequency range is more than 1 octave, both even-order harmonics and intermodulation products can occur within the range of interest. This graph illustrates the graphical definition of second and third-order intercept points at both the input and output of an amplifier. These are IP2 inches, IP3 inches, IP2 out, and IP3 out. Similar to higher-order harmonics, a change in the level of the two sinusoidal carriers at the input by delta dB will cause the level of the intermodulation product to change by n-quit delta dB. Specifications for the level differences between intermodulation products and the fundamentals must include the amplifier's output level. Without this, no statement can be made about its linearity. The formula for the nth-order intercept point reference to the input is displayed. The formula includes the input intercept point, the level difference of the intermodulation product, and the input signal level. Typically, the intercept points of the second and third order are specified. They are abbreviated as IP2 or SOI for second order, and IP3 or TOI for third order intercept. The second order intercept point, IP2 in or IP2 out, is the fictitious level at which the second-order intermodulation product would have the same level as the fundamental at the output of the two-port. Similarly, the third-order intercept point, IP3 in or IP3 out, is the fictitious level where the third-order intermodulation product would match the fundamental level at the two-port's output. Here are the formulas for the second and third-order input intercept points. The output intercept points can be calculated by adding the two-port's gain to the input intercept points. Finally, the formulas for the second and third-order output intercept points are presented. Second-order intermodulation products and the second harmonic are due to the square component of the nonlinear transfer function. A fixed correlation exists between SHI and IP2. Before you move on to the next course module, please answer the following short quiz to assess your acquired knowledge. Congratulations! You have completed this part of the course and are now ready to proceed to the next course module.